In part 3, we learned how to do polynomial division. Sometimes we can find the remainder of polynomial division without actually performing the steps of a division. We use the remainder theorem to accomplish that. It is useful in a few applications dealing with mathematics. For example, you can evaluate polynomials easily using that. We will not study this application, but it is possible to do that. We can also use the remainder theorem to prove what is called the factor theorem, which we will study in a future part. Let us briefly review polynomial division. Let us look at an example of polynomial division from what we had studied in part 3. We divide this big polynomial on the left side by x minus 1. We'll look at x and say what should x be multiplied by to get 3x power 4. It needs to be multiplied by 3x cubed to get 3x power 4. So we will multiply x by 3x power 3 and also minus 1 by 3x power 3 to get 3x power 4 minus 3x cubed. If we subtract it from the big polynomial at the top, we get minus x cubed minus 3x minus 1. We can continue in this manner. We have shown all the steps in part 3. You can review it if you want to. Finally, the remainder is minus 5. Okay. So this polynomial can be written as x minus 1 times the quotient minus 5. What we want to do is we want to check, can we figure out that the remainder is minus 5 without doing this complicated division? The remainder theorem helps us do that. The remainder theorem deals with a polynomial that has a degree equal to 1 or higher. Because if the degree is 0, it's just a constant. And let us say a is some real number. If p of x is divided by x minus a, then the remainder theorem says that the remainder is p of a. We can calculate this without actually doing the division to find the remainder. When you see some complicated mathematical definition or theorem, it is good to get some understanding of it by doing some example. Let us look at the example where p of x is 3x power 4 minus 4x cubed minus 3x minus 1, and we are dividing it by x minus 1. Instead of dividing by x minus a, we are dividing by x minus 1. If you compare the two expressions, what should a be? A should be equal to 1 because instead of a, I have a 1 there. The remainder theorem says that the remainder will be p of 1. Okay, that is in the polynomial, wherever I see a x, I replace it by 1. Okay, so I have 3, 1 power 4, minus 4 times 1 power 3 like that. So if I do this addition, I will actually get a remainder of minus 5. We know this is correct because we saw from the previous example that when I divide by x minus 1, the remainder is minus 5 for this polynomial. So now at least we understand what the remainder theorem is saying. Now let us prove the theorem. Before writing a proof for a theorem, it is good to get an idea of why the theorem is correct by doing some small example. We'll look at the same polynomial we had earlier. I can write it as x minus 1 times the quotient plus the remainder. Right? So now if I evaluate the polynomial at x equals 1, that is, I'm trying to find p of 1. Okay? If I look at the right side of the above equation, instead of x I have 1, so it becomes 1 minus 1 times the quotient minus 5. Now 1 minus 1 is 0, so 1 minus 1 times the quotient is going to be 0. Right? So I'm left with only the remainder, which is minus 5. Okay. So the basic idea behind the proof is that when I have x minus a and I use the value of a for x, then a minus a becomes 0. So when it multiplies by the quotient, that is going to be 0, only the remainder is left. Now we will write the formal proof using this idea. Dividing p of x by x minus a, let q be the quotient and r the remainder. The remainder has to be a constant because x minus a has degree 1, the remainder has to have a lower degree, which is degree 0. The only number that has a polynomial that has a degree 0 is a constant. Okay. So p of x can be written as x minus a times the quotient plus the remainder. So if the value of x is a, then x minus a becomes a minus a, okay, which is 0. So when it's 0 multiplies q of x, that is also 0. So I'm left with only r. Okay. So this shows that p of a is the remainder r. We will do an example that is slightly more complex than the previous examples we have seen. I'm going to divide the polynomial by 2x plus 1. You might wonder, how do I apply the remainder theorem? Because the remainder theorem says, what should I do when I divide by x minus something, right? But here I have 2x, okay? Note that if px is 2x plus 1 times the quotient plus remainder, if I divide by 2x plus 1, okay? So I can write the same thing as p of x equals 2 times x plus half times qx, because 2 times x plus half becomes 2x plus 1. Okay? So now the x plus half part is of the form x minus a. Okay? So I can apply the remainder theorem. Okay? So compute the remainder of p of x when I actually divide by x plus half. Okay? So what should the value of a be? Remember, x minus a should be the same as x plus half. So what value of a will give me x minus a as x plus half? A should be minus half, because x minus half is the same as x plus half. Okay. One way of thinking of it is you can say x plus half should be equal to 0. For what value of x is x plus half equal to 0? If x is minus half, x plus half is equal to 0. Okay, so a equals minus half is the correct value of a. Now the remainder is just p of a. So in the polynomial, I substitute the value of minus half for a. So this says, instead of x I have minus half, instead of 3x squared I have 3 minus half squared, and then I have a minus 1. Note that square of minus half is just 1 by 4. Okay? So if you do this additions and subtractions, you will get p of a equals minus 3 by 4. We will do one more example which shows you different ways in which people can ask you this question. They can ask you, is 4t cubed plus 4t squared minus t minus 1 a multiple of 2t plus 1? They can ask the same question as, is 2t plus 1 a factor of 4t cubed plus 4t squared minus t minus 1? This is the same as asking, is the remainder of dividing this polynomial by 2t plus 1 0? Because if the remainder on this division is 0, that means 2t plus 1 is a factor of this big polynomial. Okay? Which is the same as saying the big polynomial is a multiple of 2t plus 1. So since I'm only asking you for the remainder, checking if the remainder is 0, this is the same question as applying the remainder theorem. Okay? So if you're dividing by 2t plus 1, what should the value of a be? Remember same idea we used last time? Okay? We have 2t plus 1, which looks complicated, but we just have to ask ourselves, for what value of t is 2t plus 1 equal to 0? It is 0 when a is minus half, because we can write 2t plus 1 as 2 times t plus half. So if t is minus half, then minus half plus half becomes 0. Okay. So to find the remainder, I had to compute p of a. I had to evaluate the polynomial when a has the value minus half. I'll substitute t is equal to minus half, and I get some expression. If I evaluate it, it turns out to be 0. Since the remainder is 0, p of t is a multiple of 2t plus 1. You can also say 2t plus 1 is a factor of this big polynomial 4t cubed plus 4t squared minus t minus 1. Let us recollect what we have learned today. We have learned how to prove the remainder theorem. If a polynomial has to be divided by a linear polynomial, they have figured out how to find the remainder without actually doing the division. We also learned how to check if a linear polynomial is a factor of a given polynomial.